In our previous lecture, we have derived the Newton-Cotes formulas from numerical integration. Out of this class, we have also derived the first two formulas, the trapezoidal rule and the Simpsons rule. Let us just see what are these two formulas that we have derived. The first formula that we have derived is the trapezoidal rule, in which the step length h is taken as the total length, that is b minus a, and we have derived the formula as integral a to b fx dx is equal to h by 2 of f of x naught plus f of x 1, where x naught is our a and x 1 is equal to our b. We have also derived the error expression for this. The error expression, which we have written it as r 1, that is minus h cubed by 12 f double dash of eta, where eta is any number between a and b. From this we concluded that the trapezoidal rule integrates exactly polynomials of degree less than or equal to 1. That can be observed from this, that the error term contains the second derivative of f, therefore, which will vanish when f x is a polynomial of degree less than or equal to 1. Now, then we consider the Simpsons rule using 3 points. Simpsons rule, in which h is taken as b minus a by 2. So, that we have got 3 points, x naught is equal to a, x 1 is the middle point a plus b by 2, and x 2 is equal to b. Then we have derived the formula as integral a to b f x dx is h by 3 f of x naught plus 4 times f of x 1 plus f of x 2, and the corresponding error we derived it as r 3 is equal to minus h by 5 by 90 fourth derivative at some point eta a less than eta less than or equal to b. Now, from this we have concluded that because the error term contains a fourth derivative, the order of the Simpsons rule is order is 3, or which we call it also as precision 3. Therefore, Simpsons rule integrates exactly polynomials of degree less than or equal to 3. This happened because the error constant turned out to be 0, and hence the order of the formula has gone from 2 to 3. Higher order Newton-Cotes formulas can also be used. That means, using instead of 3 points we can use 4 point, 5 point and so on. The next formula is also called the Simpsons rule, but it is called Simpsons 3/8 rule if I use 4 points. That means, if I use 4 points in place of 3 that we have used over here, then that formula is usually called the Simpsons 3/8 rule. That is because the outside this bracket, instead of h by 3 I have 3 h by 8 outside the bracket, and it will be containing 4 points. However, this formula or the later formulas are not used much, because the 4 point formula is also the same order as the Simpsons 1/3 rule. Therefore, there is no point in doing extra computation, that is of evaluating one more value of f x. We have one evaluation less for the Simpsons 1/3 rule. Therefore, this is also of order 3 only, and because of this reason we do not use this formula. Newton-Cotes beyond a certain order 6, 7 or 8, the weights, that is your lambdas here, they are all positive. If you look at this, here lambda 1, lambda 0 h by 2, lambda 1 h by 2, here also this is the all are positive. Therefore, there is no errors due to cancellation. We know mostly errors also arise roundoff error because of cancellations, whereas if you go to higher order Newton-Cotes formulas, somehow the weights become negative, therefore, there is a chance of some roundoff error. Therefore, the most popular methods of numerical integration is the trapezoidal rule, Simpsons rule, and some modifications to this to get better accurate methods. Now, however, if I have an integral in which the length of the interval is large, let us say I want to integrate something like 0 to 50 f x dx. Now, I can use the trapezoidal rule, I can use Simpsons rule, but it is necessary to know how accurate it would be. The accuracy would depend by looking at its error term. If I look at this error term, this has got h cubed by 12 here, and this has got h5 by 90 here in these two formulas. When you take the step length in trapezoidal rule as 50, or you take in Simpson's rule 3 points, that is step length is 25. Now the error in Simpson's rule will be 25 to the power of 5 by 90, whereas here it is 50 to the power of 3 in this. Therefore the error itself is going to be very large in that case when the interval is large. Therefore application of the trapezoidal rule, Simpson's rule as it will give you inaccurate results when the length of the interval is very large. Therefore we modify this such that this h is sufficiently small. In other words, h would be sufficiently small if I break the interval, given interval a to b into smaller intervals and then use the corresponding formulas for each one of these integrals individually. So such formulas shall be called composite rules. So we shall call them as composite rules. So what we do here is subdivide AB into a number of intervals. Now the how many number of intervals, it depends on you how small the step length should be. So if you want a step length small, corresponding will increase it. Let us first look at the trapezoidal rule, how we are going to get the composite rule for this. Now we have seen that the trapezoidal rule uses only 2 points. Therefore the way in which we subdivide AB is immaterial for us. You can divide it into any number of parts. So let us divide AB into say n parts. Divide AB into n subintervals. That means this would imply that we are getting n plus 1 points, because this is n intervals, therefore we will have n plus 1 points. So let us take this division as subdivision as a is equal to x naught less than x1 less than x2 and so on, xn is equal to b. Then I will write the given interval into these subintervals. That means given this interval a to b fx dx, I will now write this as x naught to x1, that is your first point to this fx dx, plus integral x1 to x2 fx dx plus on xn minus 1 to xn fx dx. Furthermore, we will all these subintervals we are assuming to be equal. When we started the trapezoidal rule, it is equal. So we can still put here n equal subintervals, they are all of the same length. Therefore if I go a step behind, if there are n equal subintervals, then the length of the interval will be total length b minus a, that is the total length. There are n subintervals, so that is divided by n, that is equal to h. There are n equal subintervals, therefore b minus a divided by n is equal to h. Therefore the step length that we are talking of is now b minus a by n. So if in the previous problem, if you have got 0 to 50 and I want a step length of 0.5, I will now have 100 subintervals, 0 to 50 100 subintervals, so that step length will be 50 by 100, that is equal to 0.5. So we will have step length of half. Therefore the step length h depends on the number of subintervals that we choose. Now what we do, when once we write this as this is equal to this, I now apply the trapezoidal rule for each of these integrals independently. So I will write this as h by 2, all of them have h by 2 outside because the step length x naught x1 distance is same, x1 x2 distance is same, xn minus 1 xn distance is same. That is how we made them as equal subintervals. Therefore h by 2 outside, I will then have corresponding to this, I will have f of x naught plus f of x1, that is the formula for evaluating the first integral h by 2 of this. The formula for the second one is h by 2 of f of x 1 plus f of x 2 and so on, and the last integral will be f of x n minus 1 plus f of x n. Now, I can simplify the whole expression. You can see that there is f x 1 here, f x 1 here, they combine and become 2 times f x 1. There is f x 2 here, there will be f x 2 here, they combine. Similarly, I have f x n minus 1, there will be f x n minus 1 here. So, all of them will be multiplied by a factor of 2. So, I will have here h divided by 2 f of x naught plus 2 times f of x 1, f of x 2, f of x n minus 1 plus f of x n. Now, you can see that this is the first ordinate with a multiplied factor 1, the last ordinate with multiplicative factor 1 only, but all the middle ordinates are multiplied by 2. So, 2 times of this one. So, this is called the composite trapezoidal rule. And the effect of the error, we must be able to write down the effect of the error on the trapezoidal rule. Now, let us write down the error. What would be for this? I would write down the contribution of each one of them individually. We had earlier obtained the trapezoidal rule error at minus h cubed by 3 f double dash of eta. Now, I will have eta 1, eta 2, eta 3 corresponding to each one of the subintervals. So, I would therefore have h cubed by 12 f double dash of eta 1 plus f double dash of eta 2. There are n subintervals, therefore, I will have eta n, where eta 1 lies in the first interval and so on, x n minus 1 less than eta n less than x n. So, each one of them would lie in that particular interval. Now, it is easier for us now to write down what is the bound on this error. So, I can just take the magnitude of this as magnitude of r 1. This will be less than or equal to h cubed by 12, h cubed by 12. Let us take the maximum of f double dash over the entire interval as some m 2. So, let us define m 2 as the maximum of f double dash of x over the entire interval a less than x less than or equal to b. Then f double dash eta 1 is less than or equal to m 2, this is also less than or equal to m 2, this is also less than or equal to m 2, and there are n factors. Therefore, it will be n times m 2. There are n factors here, each one contributing 1 m 2, but n into h is a known value. If you look at it, this is n into h is b minus a. So, we would like to throw away this n should not come into picture here. So, out of this n h cubed, n into h will be replaced by b minus a. Therefore, this is same as, I will put equal now, b minus a, that is n into h is equal to b minus a, h square by 12 m 2, b minus a h square by 12. It is independent of the number of intervals, except that b minus a is the total length of the interval. Therefore, in practical computation, the order of the formula is still 1, because this is m 2, this is second derivative. Therefore, order of the formula is the same, that is 1. It is going to integrate polynomials of degree 1 only. But now, if you look at this power of h, this power of h is the one that shows really how the trapezoidal rule is behaving. In the earlier case, when it is very rough, it is, we are showing it as h cubed, but h cubed has no meaning when h is very large, but here h is small. Therefore, the trapezoidal rule is really behaving like an order of h square expression, and it is integrating polynomials of degree less than or equal to 1 exactly. Therefore, this is the expression which we are going to use later on when we say that we are using composite rule to get still better results. Now, while doing the numerical differentiation, we were repeatedly cautioning against the roundoff errors, that it is possible that the roundoff error can actually swallow the actual solution, and finally we may have very bad results. But let us see what would happen here in the roundoff error. Let us first see what is the effect of the roundoff error in the trapezoidal rule. So let us see what would be the effect of roundoff error, effect of roundoff. So our I, the value of the integral h by 2, let us write down f naught plus epsilon naught, that is corresponding to this roundoff error corresponding to the first one, plus 2 times corresponding to f x 1 we have f 1 plus epsilon 1 plus so on. Corresponding to this we have f n minus 1 plus epsilon n minus 1 plus f n plus epsilon n, and add to this the truncation error h cubed by 12, that we have it here, this expression, that is your f double dash eta 1 plus so on f double dash of eta n. This is how our integration rule is going to look up when we include your roundoff error and the truncation error in this particular expression. Now this is equal to our h by 2 of f naught 2 times f 1 plus f 2 plus so on f n minus 1 plus f n plus roundoff error plus truncation error. So this is our actual formula that we are using, and to this we are going to add our roundoff error and the truncation error. Now we have already derived the truncation error here, so the truncation error bound is here. So the magnitude of the truncation error is less than or equal to h square b minus a by 12 m 2. This is the bound for the truncation error. Now let us write down roundoff error. Roundoff error is h by 2, outside h by 2 I have epsilon naught 2 times epsilon 1 epsilon 2 epsilon n minus 1 plus epsilon n. This is our roundoff error from here. Now let us write down its magnitude also. Let us put the magnitude. Now if I denote by epsilon the maximum of all these epsilon i's, if I take this maximum of this, then this will be less than or equal to h by 2, epsilon comes out. So I will have 1 2 into 1 plus 1 plus so on 1 plus 1 into epsilon. I have taken now common epsilon throughout, and I have here 2 into 1 plus 1 and so on. Now the total number of points are n plus 1 points, therefore the number of these are n minus 1, because this is 1 point, so n plus 1 minus 2, so these are n minus 1 quantity. So this will be equal to h by 2 1 plus 2 times n minus 1 plus 1 into epsilon. This is 2n minus 2, 2 cancels, I will have 2n, 2 also cancels, I will simply have nh into epsilon. But n into h is b minus a, therefore this is b minus a into epsilon. Now you can see that we really do not have to worry at all about the roundoff error. The integration is a quite stable process, because the error at the most is multiplied by b minus a. If you have taken 10 plus accuracy all the effects, at the most if the length of the interval is say 50 or each one of them is say 10, so you are just multiplying 10 times that particular epsilon that we have got. Therefore we are quite safe with respect to the roundoff error. Roundoff error here really does not affect that much as in the numerical differentiation, and hence we normally say that numerical integration is usually a stable process, unlike numerical differentiation which can often be an unstable process. The same thing is true whether I consider the Simpsons rule or any of the other Newton Cotes formulas. Now let us derive the composite Simpsons rule. Let us derive the composite Simpsons rule. Now when we derive the Simpsons rule required 3 points, and we have taken h is equal to b minus a by 2. So I need for each subinterval 3 points. That means I should have only odd number of points in order that the Simpsons rule can be extended. Odd number of rules means we must have even number of subintervals. So therefore to derive the composite Simpsons rule, we divide AB into even number of subintervals. So divide AB into even number of, let us take that as 2n, even number of equal subintervals. That means we are taking b minus a divided by 2n is equal to h. We are taking 2n subintervals, therefore b minus a by 2n will be h, and therefore we have the points a is equal to x naught less than x1 less than x2, so on, x2n is equal to b. So that we have total of 2n plus 1 points. Of course this is our x naught plus 2n into h, that is you have got b is equal to a plus 2n h. So this is x naught plus h, x naught plus 2h, and so on, we have x naught plus 2h, all of them are equal subintervals. Therefore we divide I integral a to b f x dx as equal to, each one of them should contain 3 points. Therefore I would take the first integral as x naught to x2 f x dx, then the next one integral from starting from x2 to x4 f x dx, and the last interval will be x 2n minus 1 2n minus 2 to x 2n f x dx. Now when once you have subdivided into this, on each one of them now I can use the Simpsons rule. Therefore if I apply the Simpsons rule and each one is subdivided into 3 parts, therefore that is which is nothing but h. Therefore step length here in all the integrals is the same. Therefore I would have h divided by 3, this is f naught plus 4 f1 plus f2, that is the contribution of the first integral, plus the contribution of second integral starting x2 to x4, that is f2 plus 4 times f3 plus f4 plus so on. From the last integral we will have f2n minus 2 4 times f2n minus 1 plus f2n. Now we can simplify this and write this as h by 3, or let us write down I is equal to h by 3 f naught. Now you can see that the odd suffixes of f all are multiplied by 4, f1, f3, f5, f7 up to f2n minus 1, all the odd suffixes ordinates they are all multiplied by 4. So we will have this as f1 plus f3 plus f5 so on f2n minus 1, except the first and the last, all the even suffixes are multiplied by 2, f2 there are 2 of them, f4 there are 2 of them. So all the even numbered suffixes are multiplied by 2, f2 f4 plus so on f2n minus 2, and the last one again is simply f2n. Therefore, this is the first ordinate, this is the last ordinate, they have only multiplicative factor of 1, all the odd number suffixes ordinates have multiplied by 4, and the even numbered suffixes ordinates have got a factor of 2. So, this is called the composite Simpsons rule. Let us also obtain the expression for the error in the composite rule, so that we can make some comments about the behavior of the error. Now, let us write down the error R3. We had written it as minus h5 by 90 minus h5 divided by 90 of fourth derivative at some eta, fourth derivative at eta 1, fourth derivative at eta 2, fourth derivative at eta n. Now, they are divided into 2n equal subintervals to have the 2n plus 1 points, but each interval is containing 3 points. Total number of integrals that we have are only n integrals. Therefore, each one will contribute one of these terms as eta 1, eta 2, eta 3, eta n, where eta 1 is lying in the first interval x 0 to x 2 and so on. The last one eta n lies in this interval x 2 n. So, each of these integrals containing 3 points. Therefore, I can now bound this also and write magnitude of R3 is less than or equal to, again let us denote by M4 the maximum of the fourth derivative in the interval, given interval a is less than x less than or equal to b. Then I can write this h to the power of 5 by 90 into n times M4. There are n of these terms, so each one will be contributing 1, so n times M4. Again you can see n into h is b minus a by 2. So, we will have here n into h is equal to b minus a by 2, that is the expression here. So, I would throw away n into h from here, so that I will have here h to the power of 4 by 180, this is 2 coming from here M4 into b minus a, into b minus a. Let me write it once more here. That is equal to b minus a into h to the power of 4 by 180 M4. This is the actual indicator of the error in the composite Simpsons rule, and it is therefore of the order of h to the power of 4, and integrates of course polynomials of degree less than or equal to 3, because we have got M4 which is nothing but the fourth derivative. Therefore, Simpsons rule in the composite form also integrates polynomials of degree less than or equal to 3. However, this is the real indicator of the error, because now h is going to be sufficiently small, very often much less than 1. Therefore, the actual error, truncation error in the Simpsons rule is going to be very small, because this h to the power of 4. If you take h is equal to 0.1, this itself is going to 10 to the power minus 4. Therefore, the error is, even though b minus a is large, even then the error is going to be extremely small. Now, let us first take an example on this. So, let us take an example. Let us say evaluate 0 to 1 x upon x cubed plus 10 using trapezoidal and Simpsons rules with, let us fix the number of points. Either we fix the number of points or you fix the number of subintervals. With the number of points taken as 3, 5 and 9. Now here f(x) is x upon x cubed plus 10. Now let us first take the results for the trapezoidal rule. Let us take the number of points as 3. That means n is equal to 2. If I take 3 points of the interval 0 to 1, what we are really talking of is the 3 points as 0, half and 1. H is equal to b minus a by 2, that is equal to 1 by 2. So the step length that we are taking is h is b minus a by 2, that is, and 3 points are 0, half and 1. Therefore the value of the integral would be I is equal to h by 2, that is 1 by 4, f of at x naught, f of 0, 2 times f at half plus f at 1, f at x naught plus 2 times f at x 1 plus f at x 2, that will be the value of the integral. So let us now substitute. So we would get here 1 upon 4, f x is this, therefore at x is 0, this is 0, 2 times half 1 by 8 plus 10, I am just writing it x is equal to half as it is, plus x is equal to 1, this is 1 upon 11, it gives 1 upon 11. Now I will give you the value of this, it is 0.04741863. Now I am giving it intentionally say 8 decimal places because I want to use this later on for some other purpose. So let us write it in 8 decimal places. This is the result obtained by using 3 points and the composite trapezoidal rule. Now let us take 5 and 9 also. So let us take points as 5. Therefore this is simple mechanical application now, that is n is equal to 4, h is equal to b minus a by 4, that is equal to 1 by 4, b minus a by n, that is 1 by 4. Therefore the points are 0, 1 by 4, retain it as 2 by 4, 3 by 4 and 1. Now when we are actually doing in a class or a test or anything, we can retain the values of the previous one, we should write down all the values because they are all repeated, because this is a point which is already occurred earlier for us 0, half and 1. So the computation that you have performed, that is finding f x, should be retained so that we do not repeat those computations again. So we really, to apply this 5 point formula, I need to compute only these 2 values of f x, 1 by 4 and 3 by 4, and the remaining 3 values are available in the previous step itself. Now therefore I will be equal to h divided by 2, that is 1 by 8, f at 0 2 times, now this is f at 1 by 4 plus f at 2 by 4 plus f at 3 by 4 plus f at 1. So the ordinates, the middle ordinates are all multiplied by a factor of 2 and the first and the last stay as it is. Now this is simple computation, so I will give you the value for this one. This turns out to be 0.04794057. Now consider the case with 9 points. Let us take points as equal to 9, that is n is equal to 8, h is equal to b minus a by n, that is equal to 8, that is 1 upon 8. Therefore we will now have the points as 0, 1 by 8, 2 by 8, 3 by 8, 4 by 8, 5 by 8, 6 by 8, 7 by 8 and 8 by 8, that is equal to 1. Now, as I mentioned earlier, now all these 5 points are going to appear here again. Therefore, this is the one point, that is equal to 1 by 2, you have got 1 also, you have your 1 by 4 is available and this 3 by 4 is available. So, these 5 values are available from the previous step. So, I need to do only these 4 ordinates to be computed at this particular stage. Therefore, I will have the value of the integral is equal to h upon 2, h is 1 by 8, therefore 1 upon 16. I will have f of 0 2 times f of 1 by 8 so on up to f of 7 by 8 plus f of 1. And this value is 0.04807248. Now, let us give the application of the Simpsons rule. Let us take the Simpsons rule. The question was formulated such that you can use the Simpsons rule. We have been asked to take 3 points, 5 points and 9 points. They are all odd number of points. So, Simpsons rule can be applied on those points. Therefore, the Simpsons rule we have, let us take the first one, points as 3. Therefore, the points are 0, half and 1 and h is equal to half. That is the distance between this. Therefore, I is equal to h by 3. So, we will have 1 by 6 f naught plus 4 times f at half plus f at 1. Now, again I will leave this computation to you. This comes out to be 0.480733. Now, I go to 5 points. So, I have the 5 points as 1 by 4, 2 by 4, 3 by 4 and 1. So, that h is equal to 1 upon 4. We use these 5 points and write the given integral into 2 integrals each containing 3 points. Therefore, h is the step length that we are using there. Therefore, the value of the integral is h by 3, that is 1 by 12 of f of 0 4 times f of 1 by 4 plus f of 3 by 4, 4 times this odd suffixed ones plus 2 times f of the even suffix ordinate, that is this, plus f of 1. This is 1 and 3, these are the ones multiplied by 4, this is 2 and is multiplied by a factor of 2. So, this value is, I will give you the value as 0.481145. Now, let us take 9 points. So, we will again have the points as 1 by 8, 2 by 8, 3 by 8, 4 by 8, 5 by 8, 6 by 8, 7 by 8 and 1. So, that h is equal to 1 by 8. Therefore, our value of the integral is h divided by 3, therefore 1 by 24, f of 0 4 times all the odd suffixed ones, that is your 1 by 8, 3 by 8, 5 by 8, 7 by 8. So, this will be f of 1 by 8 plus f of 3 by 8 plus f of 5 by 8 plus f of 7 by 8, then 2 times the even ones. So, even one is 2 by 8, 4 by 8, 6 by 8. So, we will have f of 2 by 8, f of 4 by 8 plus f of 6 by 8 plus f of 1. I can make this computation and I get this as 0.481165. Now, we mentioned just now that in practice we do not use any higher order formulas beyond the Simpsons rule or Simpsons 38 rule. The one important reason is that we can apply the extrapolation that we talked of in the numerical differentiation can be carried over directly to numerical integration. The extrapolation idea of extrapolation depends on write down the error expression for the given method, manipulate the computed results such that the new value comes out to be order higher than what we have obtained in the previous case. Now, therefore, if I want to obtain the extrapolation procedures for this, it is not called Richardson extrapolation, here it is a different name, it is called Romberg integration. So, let us define what is our extrapolation for this. It is called Romberg integration. Now, what we really need here is the expression for the error for the trapezoidal rule and the Simpsons rule, and that would come from looking at this the truncation error for the composite Simpsons rule, and that has got factor h square. So, the leading term of the error for the trapezoidal rule is h square, and I can show that the next term h cubed will vanish, h5 will vanish, and so on. I will take that result only, so that I will have for the trapezoidal rule the expression for the truncation error as this: I is equal to I will call it as T for trapezoidal rule, that will be C1 h square, that this part we have proved, this part we have proved. So, now I will take the remaining things as h4, C3, h6, and so on. All the coefficients of the odd powers of h vanish, whereas for the Simpsons rule I is equal to I Simpson, and for the Simpsons rule we have shown that the error is starting with h to the power of 4. So, it starts with h to the power of 4. So, I will have here is C1 h to the power of 4 plus C2 h to the power of 6. Again here odd powers, all of them cancel here. Now, if this is the result, then we know what is the extrapolation procedure. When once this is h square h4 h6, we have already derived the formula for this. So, I can just carry over the extrapolation formula to this. Therefore, let us write down what is the extrapolation for trapezoidal rule. Extrapolation formulas, that is for T trapezoidal rule is it is h square, therefore, we are talking of we are reducing h, we are taking h by 2 square and so on. We are assuming that we are decreasing by a factor of 2 each time that we are computing. Then we have shown that this will be nothing but 4 to the power of m, because when h is reduced by a factor of 2, that is you are going to have 2 square, that is 4. So, multiplied by 4, 4 the previous value I t m minus 1 h by 2 minus m minus 1 h divided by 4 to the power of m minus 1. M is going from 1, 2, 3 and so on. Therefore, the first column of extrapolation will have 4 times this next value minus the previous value divided by 4 minus 1 3. The next value m is 2, 16 minus 1, this is 15, and if you have one more then we will have 4 cubed, 64 minus 1 and 63. Now, whereas your Simpsons rule starts with h to the power of 4. So, let us push this by 1. So, 4 to the power of m plus 1, let us make it, and this is I Simpson m minus 1 h by 2 minus I Simpson m minus 1 of h by 4 to the power of m plus 1 minus 1, m again going from 1 to and so on. Now, this is the formula that we can apply. Now, it is for this reason that we have done the previous example to the number of 8 places, so that we can use the Romberg integration on the example that we have done there. So, let us take this as an example. Apply Romberg integration. To the previous example. Now, we just go back to the values that we have obtained for the trapezoidal rule. So, what we are starting here is the step length, that is we have here. Let us first take the trapezoidal rule. Trapezoidal rule. The order of the formula is h square. The first extrapolation gives me order of h to the power of 4, and the second extrapolation gives me order of h to the power of 6. We have done the example with starting with h is equal to half, the 3 point formula. So, your first value of this is equal to half, then we had 1 by 4 and we had 1 by 8. These are the 3 values which we have used, and these are the values I want retained it there. This is the value that we obtained for this one, that is 04741863. Then the next value was this 0.04794057, and the third value was this 7248. Therefore, this column values will be obtained from the formula this for m is equal to 1. So, that is 4 times this value minus previous value by 3. In the next one element will be 4 times this value minus this divided by 3. So, this will be 4 times this value minus the previous value divided by 3. This is your h by 2 corresponding to this, and this is corresponding to h. Therefore, if I multiply this by 4, subtract divided by 3, and this value I will give you as 0.4811,455. Similarly, 4 times this minus this divided by 3 gives me 0.4811,645. Now, the second column would come from this formula by putting m is equal to 2, the next step, that is equal to 16 minus 1 by 15. So, I will have here 16 times, you can call it as I 1 h by 2 minus I 1 h by 15. So, I just multiply this by 16, subtract and divide by 15. I will get here 0.4811657. This result is actually correct up to this last decimal place, except this last decimal place it is correct to 7 decimal places. As we have observed in the numerical differentiation, here also the Romberg integration along with these formulas can really work wonders in getting the resolution very fast. In fact, in an example you can take a very complicated examples. If it takes about few thousands of points to get a certain accuracy, say 10 to the power minus 6, by using Romberg integration you can get it in few hundreds of points. You can evaluate that integral with 50, 100, 200 and 400, 4 steps, and then when if you do the 4 steps with Simpsons rule, for example, it will be order of H4 we started with, H6, H8, H10. So, you have got a as if you obtained a formula with order of 10th order formula that you have got, that is it integrates polynomials of degree less than or equal to 10, and the value that you would obtain, the last value here in the first column will be, I mean the error from this and this will be so large that the convergence has been obtained very fast. Therefore, the Romberg integration or Richardson extrapolation in the other cases works wonders in most of these integration and differential formulas. We would stop at that.